So finding the time period, finding a time period of a satellite. So example, this is the Earth and there is a satellite which is revolving around this Earth. The distance from center, because we always take a distance from the center when object is small, like, so we can compare the distance from center to that surface of the object. So this is the distance between them if we are representing this distance by r. And what is basically r? R is the radius of Earth plus the distance, the radius of Earth plus the height above the surface of the Earth, that is equals to r. And this satellite is revolving and we want to find a time period, how much time it will take to complete one complete rotation or one revolution. So according to Newton law of gravitation, the gravitational force is there between them because there's a gravity, and an object is moving in a circular path. When object is moving in a circular path or rotating in a circular path, so there is a centripetal force. So two forces which are there, one is a gravitational force Fg and another one is centripetal. And how the gravitational force is represent, how we represent a gravitational force is equals to G mass of Earth, because one of the object is Earth, so mass of Earth, and mass of satellite is M, so mass of satellite divided by r square. What is this r? R is radius of Earth plus the height above the surface of the Earth, that is r. And what is the centripetal force? We know centripetal force is equals to mv square over r, or mr omega square. So we can substitute here. The centripetal force is mv square over r, or mr omega square, and again r, this is the r. What is this r? This is actually the total distance. So this r square and r will cancel out with each other, m will cancel out with m. So what we have G is equals to mass of Earth divided by radius and v square. Then speed. So we know speed is equals to distance over time. Speed is denoted by v. What is the distance when object move in a circular path? So the distance traveled by the object is equals to the circumference, and circumference is given by 2 pi r. And what is t? T is the time period, because it's about one complete revolution. So one complete revolution, that's called time period. So v, the speed is equals to 2 pi r divided by t. So in place of v, I can substitute 2 pi r over t. So when we solve, this will be square because v square is there. So when we solve, I'm solving it at this on the left hand side. So I can say G, the mass of Earth, radius is equals to 2 square is 4, pi square will be there, the basically the distance square divided by t square. Or if I just solve this equation, I can say t square, because we are finding a time period, so t square is equals to 4 pi square, r will be multiplied with cube, so it will become r cube divided by g and me. 4 pi square, 4 is constant, pi is constant, the gravitational constant is there, and the mass of Earth is constant, so this whole factor is constant. So when this whole factor is constant, whenever we replace the constant and proportionality sign, what we will, when we replace constant and equal to sign will replace by a proportionality sign. So we can simply say it will be t square will be proportional to r cube. And what we call this? We call this as a Kepler's law. The Kepler law is there, which is showing a relation between the time period and the distance of the satellite from the center. Or you can also say, because if I further simplify, I can also say that t is proportional to r cube by r raised to power 3 by 2 if I take a square root both sides. Is it clear? The Kepler's law. This is a formula for the Kepler, like the relation of the Kepler's law. It said like when the object will move far away, then what will happen if we double the distance? How the variation will occur? Raised to power 3 by 2 means cube will be there, like 2 cube, which will be 8, and then take a square root. So if this is double, how the variation of the time period, they are proportional to each other, but raised to power 3 by 2, so 8 under root 8, so it will increase by under root 8. Same thing, if this is multiplied by 3, so 3 square, 3 cube is there, 3 square is 9, 3 cube is 27, so it will vary with the under root 27. This is a factor by which the time period will increase. Is it clear? The Kepler's law. Then the similarities and the differences between the gravitational and electric field. So what are the similarities between the gravitational field and the electric field? First thing, they both have infinite range. Like you cannot say that the gravitational field is acting at a distance of say 3 meters, 5 meters, 20 meters. Variation is there. How the field strength will vary? The field strength will vary with the square, because if follow the inverse square law, as the distance increases, intensity decreases. So the first similarity, both have infinite range. That is one thing. And the second, both will follow inverse square law. Like the variation is inverse square law. If you remember, in an electric field, when we have two charges, say two charges q1 and q2, and they are separated by distance d. So according to Coulomb's law, F is equals to k q1 q2 over r square. Or if the distance is d, then it will be d square. And if we have two masses m1 and m2, and the distance between the center is d, so according to the Newton law of gravitation, that force between them is g m1 m2 over the distance, the square of the distance between. So you both of them, you can see the variation of the force. It follow inverse square law. The other one also follow inverse square law. These are similarity, and both have infinite range. Like you cannot limit to the region where there is gravitational force. Infinite range is there to infinity. Like we cannot define that the range for gravitational, or even like for example you're sitting at on a chair, so still you're feeling, still there is a force of gravity from different regions, different parts, different planets on you. In the magnitude is small, but still there you are experiencing the force of the gravity. And what are the differences between them? Number one, gravitational field is always attractive. Gravitational field cannot be repulsive. It is always attractive. But electric can be, because like example, like charges repel each other unlike attract. So but electric field can be attractive or repulsive. So both possibilities are there, both ways that the field can affect. For electric, it can be attractive, repulsive, but gravitation is always attractive. And the origin of these fields, like the gravitational field, are the region in which the masses experience a force. And electric field is a region where the charges experience a force. So the gravitational field is for masses. When there is a mass, there is a matter, there is a gravitational force. And electric is for charges. Then electric field can be attractive, repulsive. That point we already discussed. And there is also, in electric field we can shield the object, but gravitational field there is no shielding. So no shielding in gravitational, but electric can be shielded. What is the meaning of this? Like example, if you have two masses m1 and m2, and you place a small object here, a small matter, negligible, like very small mass, what happen, even though you add another matter, another material within the space, if this mass was experiencing example 10 Newton force, still it will experience 10 Newton force. It cannot be shielded. Like, but what happened in electric one, if you place two charges, like charges are there, like charges repel each other, so they try to cancel out each other. So I can have a region where this mass, where this charge, if I place a charge here at point A, this charge is shielded. Why? Because the two electric fields are cancelling out the effect of each other. So when I place a charge in the region where there is no electric field, so that even there is a charged particle, it will not experience, or it will not move in any direction, or resultant force on the charged particle will be zero. So electric field can be shielded, like the charges can be shielded within the electric field. So objects can be shielded from electric field but not from gravitational field. And the force between the unit charge is separated, is much stronger than the force between the unit masses. Like when we compare the values, the strength of the field, if I say I have two objects which are having a same, the value of the k, when you compare the value of the k, the value of the k is 9 exponent 9, and value of the g is it was 6 point into 10 to power minus 11. 6.7, yeah. 6.7. So when you have, for example, you have a unit mass and you have a unit charge, so you can clearly see that the value of the k, because if I say all these factors are kept constant, m1, m2 and d square all are kept constant, so means the force is proportional to the constant value. The gravitational constant is very small as compared to the uh, coulombs, the constant used in a coulomb equation, which is having a higher value. So when we compare the strength of the force between the unit charges at a same distance is stronger as compared to unit masses. Or you can simply say, when I say unit mass or unit charge, it means we want to compare, keep all the factors same, and just if find the effect of constant on the value of the f. So you can simply say gravitational or electric field is stronger for unit charges at same distance compared to unit mass. So, like example, if you have 1 kilogram, two objects, each of mass 1 kilogram, separated by some distance, and we have two charges, unit charges, 1 coulomb, and separated by the same distance as the masses. So, gravitational electric field will be much stronger as compared to gravitational field. So, this is a comparison between the electric and gravitational. Is it clear? Then, if we want to find, because this topic is about cosmology and astrophysics, so if we want to find the distance between the planets, stars, and galaxies, so there are different methods. So we can use different methods to find. So what we can use different techniques. We can use a Kepler third law. Kepler laws are there about the motion of these astronomical objects. So we can use a Kepler third law. The Kepler third law is the same one which we derive a formula that t square is proportional to r cube. That formula we can use that, because if we know the time period, and what is this r? This r is actually a distance. We can relate, because it's not like directly we'll get the answer. We will relate the things and we'll find the distance. We can use this. This is one of the method. We can use trigonometric parallax. This is one of the method we'll discuss in detail. We can use Hubble's law. And we can also use the radar measurements, like using a radio telescope. We can collect the data information about this, the temperature of the star, the wavelength it is emitting out, and using that we can work out the distance between the star and the earth, or difference between the planets and the earth, or the distance between the two stars. So we'll discuss this in the detail. I'll share another link